Bon dia. Welcome, everybody. It's a pleasure for me to welcome Dr. Sergio Pablo García Carrillo. He's a former member of this university for some time, let's say, but afterwards he undertook the PhD at the Institut Químic de Sarrià under the supervision of our colleague Núria López, where he focused on chemoinformatics, automation, and machine learning techniques for theoretical heterogeneous catalysis. After his PhD, he joined the University of Toronto as a postdoctoral researcher, where his work centered on laboratory automation and device integration for self-driving laboratories. His current research interests span the automation of both computational and experimental chemistry, data management, and chemistry digitalization, and their integration with artificial intelligence. So today he will give a lecture on the artificial intelligence powered self-driving laboratories for accelerated discovery that he's doing at the Acceleration Consortium of the University of Toronto.
Yeah, thank you for the presentation. Just a small thing. I'm from Institut Català de Investigació Química, not Sarrià. Just that. So, oh, is this working? Oh, it's working? Okay. So yeah, I did my PhD at the Institut Català de Investigació Química. During my PhD, I was researching on trying to automate the different computations that we were doing to assess the heterogeneous catalysts. So what I was trying to do is to fully automate all the creation, the building of the different geometries, and also the computations that we were doing in an HPC. We were working in a very traditional manner, and I was trying to create the software to generate the structures, do the computations, and then afterwards compute gather the results and parse the results, and then provide them to the user to try to accelerate what we were doing there. After this, I was also working on trying to integrate machine learning to this to heterogeneous catalysis, because we were able to obtain a lot of data from the automation that I was performing on the different just like systems that we were studying. After that, when I was in my final year, I moved to Toronto because I got a grant to just like visit Alan Asperger's group at the University of Toronto. And then we started doing research on the use of graph neural networks for the estimation of binding energies for heterogeneous catalysis. Our target was to use small molecules to try to predict the binding energy of big molecules. For that, we were transforming the molecules into graphs, and we were trying, we were training the system only with small molecules, and then trying to predict the energy of molecules that we were not able to compute because they were too big to be computed in an HPC center. So after that, I got an offer to work at the University of Toronto as a postdoctoral researcher. But as I was working always with theory, I wanted to switch my path and then start working more with the things that are really happening in the laboratory. Because when I was doing my PhD, I was collaborating with a lot of scientists, and the problem is that most of the times you need to combine both theory and experiments, and I was not aware about the experiments that they were doing in the laboratory. So when I went to that laboratory, I found that there is there is a current topic of research that are self-driving laboratories. These laboratories are composed mainly to two different moieties that are automated hardware and the experimental planner. The automated hardware are the robots that are in the laboratory. These are the ones in charge of automating the experiments. These can move just like different parts of the laboratory. They can also move between different laboratories, or they can be static setups that are just like chemical reactors and so that are fully automated. They do not need to be robots. So, so there are many just like hardware that you can choose from. You have just like a specialized hardware for different methodologies. You have also general hardware, as for example, robot arms that can just like do many things, as for example, push buttons, or just like take different vials, for example. You can train these machines. There is a huge research topic right now. And then you have also open hardware, that is the hardware that other groups are creating around the world, that you can just like print in your 3D printer and incorporate in your laboratory. Not only the hardware, but also the software is important because most of these robotic arms work with computer vision and they will need to be working or learning from a virtual environment. So you will need to create digital twins for them. These digital twins try to do the same thing that they will be doing in the laboratory and learn from these errors in a simulated environment. So the other part of these cell-driven laboratories are the experimental planners. They are mostly AI or artificial intelligence based. This, for example, is an example of a Bayesian optimizer that is called Atlas that was published by Alan Aspergusi group this year. That their main goal is to try to optimize something that you are doing in the laboratory. For example, if you are creating new materials and you want these new materials to have a certain property, these Bayesian optimizers are able to, given a set of parameters that you will use to perform the synthesis, try to give you an advice to which is the experiment that you need to do to optimize the property that you want. For that, you will need to have the synthesis, the characterization, and finally this algorithm that will be the one that with the data for the characterization will set new parameters for the synthesis. As the synthesis is fully automated as well as the characterization, this is a closed loop that runs over and over. But I was working on just like the connection between both. My work was mainly focused on the development of an orchestrator. An orchestrator, it's the machine that is in charge of managing everything that is happening in the laboratory. Not only the automated hardware, but also the experimental planner. At the end, you will have the orchestrator. It's managing, for example, public databases, private databases. If you want to, for example, connect with HPC facilities to perform theoretical computations of different materials, you will also need to connect with external resources, and you will need to also put some kind of interface because most of the times the people in the laboratory do not know how to interact with the computers. This is not true for computational chemists, but for the laboratory, I will say that they are not able to communicate with the laboratory if you don't put that. So my work was mainly focused on the orchestrator, but I was also doing a little bit of work in the automated hardware and also the experimental planner. So for the laboratory orchestration, I'm now trying to deploy this orchestration in the facilities of the Acceleration Consortium. I will tell you about that at the end of the presentation. But my main goal is to have that all the laboratories will follow these schematics in which we will have a general orchestrator that will be in charge of just like communicating all the machines that we will have in the laboratory, all these automated machines that will be producing the data for the experiments that we will be performing. So we will be doing that just like using servers, creating a server for each of the machines that we connect to the laboratories in a way that the server will expose some functions to the machine and they will be able to be executed by the orchestrator. In that way, the scientist is able to just like put the different blocks and configure the laboratory and the loop that they want to do just like pretty easily or pretty intuitively. So this is an example of a workflow. For example, imagine that we have a pump and we want to just like put A in a reactor. So we just like say that we want to move A to reactor, then we save the data. We say that we want to move B to reactor, then we hit the reactor in the third step. Finally, we use the pump. We use the pump again to just like move the reactor for a IR characterization, and then when we are in the IR instrument, we perform the measurement and we store everything that is happening in all the processes. But this is not limited to all the experimental data. As I said, this is also true for computational resources. For example, if you want to use a machine learning model, or if you want to perform a simulation on the things that you are doing in the laboratory or in the study that you are doing in the laboratory, then you will need to incorporate this kind of resources as building blocks that are being connected to the orchestrator. So at the end, you will have, for example, 3 different workflows. One workflow that will be for the synthesis and measurement, another workflow that will perform, for example, machine learning that will be a machine learning model that will analyze the data that you are collecting from the characterization instruments, and then finally you will put that data on the experimental planner that will suggest another experiment based on the data that you previously trained that model with. At the end, you will repeat the loop over and over until you reach your optimization target. So I was doing that in a Spruce group with this. Well, I was trying to just like build this entire infrastructure in a Lang Spruce group in which they have a ChemSpeed platform that it's a fully automated robotic platform for synthesis. Then we have the HPLC-MS that was for detection of the different compounds that we were synthesizing in the ChemSpeed platform. And finally, we also wanted to integrate an automated optical characterization platform that was the one that was giving us the target that we wanted to optimize, because we were targeting OLEDs and we were targeting lasing efficiency. We also tried to integrate as a proof of concept a computational workflow here, in which we were using an SMILES string to generate the 3D structure and then send this estimation of the lasing efficiency to an external resource that will automatically perform all the steps and also collect the data. So at the end, we will have something like that, in which we have a first recommendation. When the first recommendation, it's both. It's in parallel performed in the laboratory, so it's synthesized in the laboratory. It's then splitted with the HPLC-MS. Then we have the characterization, and finally we get a second recommendation from the experimental planner. And we do the same with the theoretical part, including some theoretical insights to the second recommendation. So we repeat this over and over until we get our lasing efficiency. That work was done by Malcolm Sin, that was an excellent master student. So he was able to just like implement everything in the laboratory. For the experimental planner, we were using Atlas. Atlas is a set of experimental Bayesian optimizers and different just like optimization techniques for experimental chemistry that were released by Riley Hickman. That was a student of the acceleration course of Lang Spruce group. This is public, everyone can download it, and it can be integrated in any laboratory that it's automated. But we are also thinking about using this kind of software for theoretical calculations, not using only theoretical calculations and not integrating it with the experimental approach. So now in the Acceleration Consortium, what we are trying to do is not only connect one laboratory, but connect many laboratories to the orchestrator. In that way, we can also we can not only do a fully closed loop for one kind of experiment, but we can integrate the efforts of many laboratories with the drawback that we will need to do just like some transportation between the different laboratories. So another problem that you have when you are working in cell-driven laboratories is that all the equipment that you have, it's very expensive. So we were also trying to reduce the cost that for just like implement one of these laboratories in the university. Because for example, the ChemSpeed platform that I showed you before costs this. It's here. This is easier. So for example, the ChemSpeed platform that I was showing here, it's around 2 million euros. So it's quite expensive. So anyone that wants to create their own cell-driven laboratory will need to suffer from having a lot of budget or not being able to implement it. So we were trying to reduce the cost. So we found that one of the things that was commonly used in the laboratory was the potentiostat for electrochemical characterization. We were doing a lot of CVs at that moment, and we got a problem in which the potentiostat that cost like 10,000 Canadian dollars broke, and then we needed to just like send it to repair. The repair cost was around 3,000 euros, I will say, a lot. And we were 1 month without being able to perform these experiments that we were performing in a daily basis. So we decided to create our own to create our own potentiostat device, because one of the things that we want to do is to create these devices so everyone can just like download the blueprints from the internet and just like build them in their laboratory. So we tried to reduce the cost of the potentiostat. We did this, we created this small potentiostat with the help of an engineer that is Angel. And we were trying to integrate it in our laboratory in a also cheap setup. We integrated it with a very cheap synthesis platform. So for the synthesis platform, we were trying to just like create, as I said, a very cheap platform in which we have a pump and selection valves. The selection valves are just like switching the different ways that you have to reach the metal or the ligands, or well, the different ways that you have to connect the different parts of the setup, I will say. So it's like a graph if you think about it. So you can, for example, here we wanted to just like create some organometallics, just like mixing the metals and the ligands. We were just pumping them to the reactor and then trying to create creating the compound there. So we put the potentiostats, we added the potentiostats to the experimental characterization platform. These potentiostats were able to perform the electrochemical characterization of the compounds that we were obtaining from the synthesis platform. And with that, we were able also to just like collect everything in our database and save these experiments automatically. We were putting here some mechanism also to just like tell the users if something is wrong, because these tubes tend to clock time to time. This setup, this is just like the photo of the entire setup, costs around, I think that it's 3,000 euros in total. So compared with the PNSpeed platform, that I mean, they can do much more than our setup. Our setup, it's more humble, I will say, and the potentiostats are not the best of the market, but we were able to perform the electrochemical characterization of at least, I think that it was more than 300 compounds in just like 1 week, for example. So this is just like the workflow that we have. As I said, we were doing it as in parallel. So we can, with the cheap potentiostat, it was very easy to just like run the same experiment, just like twice at the same, I mean, in 2 different potentiostats at the same time. And then we were comparing the results to see if they were matching, or if something is wrong in the setup. If something it's wrong, we just like send a message to the user, and then the user is able to go there and see what's happening in the laboratory. And as I said, everything here it's fully automated, except for the clogging that we were not discovered how to just like solve that without any human intervention. So as we were having that setup, we started to think where we can just like use this kind of potentiostat, or where we can use this these techniques that we were developing, or this orchestration and everything that we were developing, to help just like in some real tasks that we are doing in the laboratory. So this is one common thing that most of the PhD students need to do when they are performing electrochemical experiments. That is that they need to polish an electrode. The electrode, it's polished always with the same shape, and they need to spend like 30 minutes to 1 hour just like polishing this electrode, as you can see here. So we said, okay, why we don't use a robot for it? For the polishing, instead of just like having a human, let's connect a robot and let's do it, and let's try to just like mimic the things that humans will do. So we designed the hand of the robot, that it's just like to try to assure that the pressure is always the same. We created also a polishing station with just like an XY motor, and then we also created a washing station and a measuring station that it's connected to a potentiostat. In that way, we wanted to check what happens to the electrode if we use it over and over. So how the electrode efficiency decreases. Well, not the efficiency, but how the characterization decreases over time when you start running the same characterization experiment over and over. So this is how the setup looks like. So we have the polishing station, we have the washing station, and then we have the measuring station. The robot it's holding the electrode there, and it's just like moving between the different stations to just like perform this polishing and just like measuring over and over. We also put a camera on there, and we were able to collect the images from all the different measurements that we did. And I want to show you first how the setup works. This is 10 times just like the speed. So we are performing now, for example, a characterization. Now we are washing it, and now we polish it. And then we go over and over until we have many data for it. So as I said, we were able to just like capture the images of the surface of the electrode, because we found that the electrode is also changing its surface once you are performing just like different cyclic voltammeters with it. And we started also collecting the data in that way that you can associate the different cyclic voltammeters that we were measuring with the photos that we were taking from it. So another thing that we ask is it's just like the shape that we were doing correct, because most of the times when you are polishing the electrodes, and we were looking a lot of bibliography, they always say that you need to polish the electrode in an 8 shape. And nobody tested that as long as we know. So we started just like trying to do that experiment with the robot, as we don't need just like a PhD student for doing it, and we can automate it. And what we found is that it doesn't matter the shape that you use, but the electrode will be polished when you have polishing, when you start just like doing it the shape that you want for 300 seconds. So last part of this talk will be about incorporating published knowledge in your setup. So one of the main problems that we have with cell laboratories is that we rely a lot on the data that we are collecting from the laboratories, but incorporating data that it's already published can be tricky, because you need to read the articles, you need to change the format of the articles for something that it's human readable and then you need to find a way to incorporate it with the models that you are using for your system. So we try to automate this process, at least just like the process of collecting data from the internet. There are a lot of databases, for example, the Open Reaction database, Reaxys, and lots of different websites that you can visit that they have a lot of structured data for many reactions, but we were working with electrochemical setups, so we were trying to collect electrochemical data. And the problem is that we found that, for example, for open reaction dataset, only 27 experiments were for electrosynthesis. So we were trying to create a model, a machine learning model that was able, a machine learning model able to parse the data from images. So this is a project that was led by Xishuan Leong. I was collaborating a little bit with her for this project, but I need to just like explain it to you because this will give you a little bit of context. So what we have here is that when you are just like looking for electrochemical experiments, you will have that they are encoded in that scheme that it's just like saying to you which are the experimental conditions of the reaction that you are performing. So the problem is that when you look at bibliography, everyone just like publishes this schemas as they want. So they don't have any standardized criteria. So at that moment, we wanted to use large language models or visual models to put that data in the model for the model to be able to extract the data and associate it to the correct environmental parameter that it's pointing to. For example, we want to just like we want to know which one is the electrode, which one is the temperature, which one is the intensity, etc. So what we did it's collect all these images from different articles that were in HTML format that were just like published in different journal web pages, and then introduce them into a machine learning model that we were training with a prompt, able to extract the information from these images. We tested it with a lot of different machine learning models, with a lot of LLM models that provide visual helpers, as for example, ChatGPT, Claude, Lava, Gemini, etc. And we found that they were quite precise when it comes to extract this information from the images. The other problematic stuff that you have with this kind of images is that most of the times the output of the outcome of the reaction comes with a footnote. And machine learning models struggle to just like put that footnote or to try to find a relationship between the footnote and the compound that you have there, or the efficiency that the electrochemical efficiency that you have there. So we were training also the model to try to split the images in image in different parts and try to associate the footnote with the name of the molecule that was in the image. We found, as with the previous one, that machine learning models are pretty good doing that with very few just like instructions. So we did that for many images and for many just like articles that we didn't know that contain just like different kind of schemas. So the final output, it's a JSON file that contains all the structure data that the LLM it's able to collect from that image that you are introducing in it. So the problem is that most of the articles are not in HTML format, and most of the web pages forbid you for retrieve the HTML file from the web page. But that's not true for PDFs. The problem with PDFs is that they are very problematic because this is the typical structure of a PDF. They have images all around there, they have tables, they have no structure. If you go to the supplementary information, it's just a hell. You cannot just like extract any data from there because there is no standardization there. So we wanted to create a tool that is able to perform the process that I told you in the last slides, but automatically for PDFs. So we started creating a tool that it's divided in 3 different modules, and each of the modules it's able to process part of the PDF. So the first one is Visual Haste. Visual Haste, it's the module that detects the images and the captions. It was trained from a visual model, so this is something that we train with a lot of images from articles that range from 1949 to 2024, because we wanted also to be able to apply this model to all articles, because most of the knowledge is also stored in this maybe all articles. And what it does is that it extracts the tables and the figures, and also it's able to split the caption from the figure. So the model it's able to read the text that it's in the caption that maybe contains the footnotes or contain information that is related to the reaction, but also it's able to split the image and associate the caption with the text. So it was pretty good. I was pretty surprised with the precision that it has. This is a pre-trained model. We released it in Hugging Face, so if anyone wants to use it, it's freely available and it runs in a laptop. The problem is that in a laptop it can be pretty slow. So the second, we tried it with many images, and it's able to just like it works with many different scenarios. There are some that if you are changing, for example, the space between lines suddenly, or if you have a table that it's just on the bottom of image, it can be tricky, but it works most of the times, I will say. So the second part is to transform all the data that we collected from the images into a format that it's machine readable, I will say. So for doing that, we created the data reader module that just like that gets the image, sends the image to the LLM model together with the caption, and tries to generate a JSON file that it's prepared for being stored in a database. So as I said, we trained this module with 3 different with 3 different data sets, one for organic electrosynthesis, photocatalysis, and organic synthesis, and the results were also pretty good. We were able to identify almost all the different reaction conditions that were explained either in the images or in the caption. So you can see at the right how it collects all the information here. Maybe the light it's not the best, but we also try to standardize the molecule. We try to convert everything to canonical smiles. We do that querying PubChem, then retrieving the information and using, I will not remember the name right now. I do not remember the name right now for the code, but it's just like canonize the smiles that we get from PubChem to be sure that everything is correct. But we are missing something. That is that all this text that we are obtaining needs to be machine actionable. So when you're using cell-driven laboratories, the cell-driven laboratories need to be able to access to a database to retrieve data. Most of that, they need to have an structured database where they can collect the data. That's true also for the scientists, because if, for example, you don't know how to query a database and you need to do it with an LLM because you don't know, just like SQL or whatever, LLMs use a technique that it's called retrieval augmented generation, in which they query a database, they collect the data from the database, and they prepare the prompt based on the data that they collect. So what we try to do as the final step is get all these JSONs and put them into a structured database. For doing that, we found that the LLM models are also very good in terms of doing the conversion between one format to another format. And they are able, just with the Python code that defines the structure of the database, plus the example that you are giving to it, for example, the JSON file with the containing all the environmental variables, it's able to do the transformation. So at the end, we were able to create a graph database with 50 different articles. The main problem that we have with this method is that it's really expensive. For example, for creating this database, we needed to spend like $200, for example, for this one. Why? Because we were working with ChatGPT, and ChatGPT is kind of expensive. But one of the things that we are considering right now is to use DeepSeek or other open source models to perform this conversion instead of relying on the API of ChatGPT. So yeah, the preprint is available. We just published this project just like a few days ago. The GitHub repository, it's available for everyone. We are trying to just like improve the quality of the code. And this project was done in collaboration with Brandon Wong, that was a graduate student from, well, not an undergraduate student of computer science at the University of Toronto. And yeah, I just like encourage you to download the model or try to use it if you want. So the last part, I didn't mention it, but I'm now a staff research scientist at the Acceleration Consortium. The Acceleration Consortium is a new research facility in the University of Toronto. We are targeting to have 7 different laboratories on different fields that will be fully automated. I'm working on the Artificial Intelligence and Automation Laboratory. We are trying to provide the tools for orchestration, for parsing the data, for performing the AI to all the laboratories. Our tools will be, we have a strong commitment with open science. So the laboratories and also the tools that we will be developing in the Artificial Intelligence and Automation Lab will be freely available. And we are trying to encourage other research groups around the world to use these techniques and try to create their own self-driving laboratories. My laboratory is not working, as I said, it's not working only on orchestration, but they are also working in robotics and also in atomistic simulation and how to use machine learning, LLMs models to try to combine everything in the laboratory, or use them as a generative models to try to accelerate the generation of new candidates for just like new materials or new compounds. This is an example of work that someone in my laboratory is doing. This is Kuros. He's working with robots, and this is a work in which he was trying to talk with the robot to tell the robot what to do and automatically create the whole workflow that it needs to do to just like to perform an electrochemical experiment. This is another project led by Merat Ansari, that it's another member of my laboratory. He's working on using LLMs as a generative models, so you don't need to use. So the model is able to say to you if you need to perform a computation, or if you need, for example, to use a model, machine learning model, to estimate the target properties that you have, instead of needing to calculate it. Trying to improve or accelerate this discovery process that we all are doing. So yeah, many thanks to all the collaboration, to all the collaborators. I've been collaborating with a lot of people from here and from external groups. Many thanks also to Alan Aspergusik and the Matter Laboratory. This is all the people that helped me when I was doing my postdoc there. And a special thanks to my brother, that was the designer of the potential stat device. He did it just like free of cost, so I'm extremely grateful for that. And to Shishua Leon that sent me the slides for the document parsing part of this presentation, as we presented this last week, and I was not able to just like do the slides so quick. So yeah, that's all. If you have any questions, I will be happy to answer.
Great talks. Any question?
No?
Thank you.
Thank you, Sergio Pablo, for this nice overview of all the things you are doing at Acceleration Consortium. So first of all, I would like to ask you a technical question. So you are dealing with many different things, with just coding robots, coding these arms, and then doing the machine learning that we are more used to do here in the institute. So you always use Python, or which kind of languages are you using to code all these things?
Yeah, most of the times we are working with Python. So when we need to communicate with the instruments, we need to use C# because the instruments are very restricted. Because when some company is selling you an instrument, they don't want you to automate the instrument. They want to just like sell you some software. And so we are constantly arguing with these companies to provide the drivers in Python, but everyone is providing them in C#. So most of the times we use Python. We try to create the Python wrappers for the C# drivers that we have for the different machines. But yeah, sometimes we need to just like do some coding in C#. For all the tools that we are developing in the Acceleration Consortium, we are trying to be 100% Python. We don't want to just like go with another language, as all the scientists around the world are using the same language, and we do not consider that we need to just like change that thing for now. So yeah, also for evaluation optimizers, the machine learning models, all the frameworks are already in Python, so we don't need to switch. I think that we don't need anything more than Python for doing everything.
And then, for instance, in the example you gave, that you are able to read the data from these papers of electrocatalysis, for instance. Are you using protocols that already existing protocols to do so, or did you innovate? So you came up with new models to do so. You are using already existing packages in Python, or how? Yeah.
So as said, we were relying a lot on the OpenAI API, because we were using a lot of ChatGPT for that project, but we made different things for that. One of them was, for example, the Florence model that we tuned, because for extracting the images from the articles, there are some models that are able to split images in segment images in different parts, depending on what they see in the image, but they were not trained for scientific literature. So we trained that model and we published it on Hugging Face. But the architecture, it's based on the Florence model that you can download for Python for free. But for example, for the graph database, that was something that I code just like manually. This was that wrapper that just like sends to ChatGPT the code and then returns the code and just like connects it to the database. That was all just like hard code by me, I will say. So it depends, but it's always Python. So most of the times you will find the right packets to do the things that you want. There is just like a small, very, just like a specific occasions where you need to just like do the code by yourself, in my experience.
Thank you, Sergio. It's very interesting, the topics about automation. I have a curiosity about the experimental part.
Hmm?
If you consider that the robots are doing all the work, the product, the final product of these experiments are improved in somehow better than the humans one?
It's more reproducible, I will say. I will not say that it's improved. So you can, for example, use an experiment. You can just like forget about the robots and you can put an experimental planner and just like give all the scientists a tablet and just like do some kind of, they need to report, and then the experimental planner will just like gather the information and will target or will say to the scientist which is the new experiment that they want to do. That will that will optimize the target more rapidly than just like the humans doing the work. Because most of the times the students will just like do some kind of combinatorial work and they will not just like be based on, I will say, I mean, they will have intuition, but sometimes they are just like doing the combinatorial one. So the experimental planner usually it's faster than the students. But for the automated part, I will not say that it's better than the students or better than the scientists, but it's 100% more reproducible. So what we want to do is that we have a setup here, we have a setup in another place around the world. So we just like have the workflow defined, we plug that workflow in another site, and the results that we are getting should be the same for both places. So this is what we are targeting. Because when you are doing an experiment and you have different PhD students, you will obtain different results. That's if you went to the just like teaching on the laboratories, that's always the same. So
One more. Do you think this protocol could be applied on industrial field?
industrial field, yeah, companies are very interested in the acceleration consortium. We are collaborating with a lot of them, and they are really interested on this kind of things, on this kind of automation, because they were dealing with a lot of combinatorial automation long time ago. Now with the Bayesian optimizers and with this kind of dynamic build of the laboratory, because we are trying to modularize the laboratory in which you can plug and play all the instruments that you have and create just like different layouts depending on the setup that you want. Most of the times when you are working with an automated robotic platform, the automated platform it's fixed. So you cannot change anything there. It's like the CAN speed. But now that the companies are just like changing their mind and are saying, okay, maybe the dynamic approach, just like combining different parts on the laboratory and using this Bayesian optimizer or these optimizers that are working will be faster than just like having our high throughput platforms in the laboratory running with a few technicians. Merck, for example, it's doing a lot of work with us on the Bayesian optimization part. So they are creating a Bayesian optimizer in collaboration with the consortium, and it's publicly available. So anyone can use it and download it. And I do believe that this will not only work with experimental setups, but also with computational setups.
Thank you.
A question from Albert Bruch online is very impressive work. When guiding experiments, I think I saw a loss function labeled as regret. Can you tell something about this?
About what, sorry?
When guiding experiments, I think I saw a loss function labeled as regret.
Loss function label. Oh, sorry, I cannot understand it.
Albert, et pots connectar si vols.
Loss function.
Hi, can you hear me?
Yes.
Yeah, so it was on the first slides. I thought you showed some examples. And it seemed like there was some kind of, when you were optimizing, here. So here you have this optimization trace, right? And I don't know, what is this regret function? So what is this, or this regret measure? I thought it was a loss function, but maybe it's something different.
No, it's a loss functions. This is a synthetic function, and then we are just like measuring regret. But it's just like because this is something synthetic. We are working with synthetic data here. We were testing the algorithm.
Okay, but what is regret exactly? So how do you measure regret?
To be honest, I was not in charge of this function, and this is the first time that I see the regret there.
Okay, sorry then. Okay, I'll just read the article then.
Next time I will use an example from my own experiments.
Okay. Anyways, very nice, very impressive work.
Yeah, sorry about it.
Just as maybe I can ask a follow-up since I'm already connected. But
Yes.
so how do you think one can? So I'm very happy that finally theoreticians are taking over the experimental world as well and trying to dominate, let's say, in this finally. So my question is, if we now wanted to transition to doing things like this, right? Where should we get started?
Where should you get started? I mean,
If we want to, as a theoretician, transition to basically starting a project like this, you know?
if you are a theoretician, I think that you can start just like right away. I mean, the only thing that you need to do is to get one package for automation of computations. One of the big one is AIDA. It's not, I will say, but it works. So the only problem that you will have is that you will need to just like connect to the queue system of the HPC facility. That's tricky. But once that is done, you can create your own workflows. And then I will suggest you to use Bayesian optimizer algorithm if you have a clear optimization target and a clear thing that you want to modify.
Okay.
Or use active learning method, in which you can just like collect the information that you're obtaining from the results and trying to use something that it's not exactly an experimental planner, but that can give you some kind of guidance on the next experiment that you want to do. But I would suggest to just like go for experimental optimizers, go for Atlas. There are a lot of packages out there for experimental planning and optimization that you can adapt quite easily for computational work.
Okay, thank you. So I am familiar with many of these, let's say, workflow managers or packages for computation, but also to take this step to do experimental ones, you would recommend first establishing some workflows and knowing what you're doing with just computations, to just waste resources on computers first, and then move to wasting materials resources.
Yes, first the thing is to get familiar with the computational work, and then there are a lot of reviews on, well, not a lot, but there are some reviews on cheap laboratory equipment. Most of the times people will start with some synthetic platforms that they see on the internet that they are cheap, or that they can start with just like something very simple, and then they can start just like growing and growing. Most of the people, it's also buying 3D printers to put custom stuff in their laboratory. And then once you have just like the expertise to connecting them with the workflows, and also the expertise of just like trying to connect your own laboratory, I think that that's a good starting point. Just like buying the expensive stuff and trying to connect everything there.
Okay, great. Thank you very much. Very exciting stuff. Thank you.
Thanks, Albert. Any other question around? If not, let's thank Sergio Pablo again. Thanks for being here.